Okay, hello everyone. I think we can start. Just guys, let me know if you see my screen.
Yeah, we can.
Okay, nice. So I think we can start right now because the meeting is recorded anyway. So if anyone is late, you can review the presentation anyway. So welcome everyone on the next AWS User Group Poland meeting. This time it is 14th online meetup in this way. Let me introduce our today's speakers, Gojko and Bogusław Buszydlik. Hello guys, I really enjoy that you have accepted the invitation for our today's meeting. So hello and warm welcome.
Hi.
Thank you.
Short introduction of myself. I am Wojciech Dąbrowski. I am working in the pattern match as a solution architect. I am also an AWS community builder and AWS user group leader of the Polish meetup. You can reach me out on the LinkedIn, GitHub, or Twitter. So don't hesitate and ask any question regarding the user group or AWS community. Short notice about questions regarding the presentations, regarding the today's presentations. When you have any questions during the sessions, don't hesitate and ask the questions on the chat, and speakers will answer those questions with pleasure after the presentation. So I hope there will be a lot of interesting questions, and we will have the short discussion after the session. And the short recap of today's agenda. At the beginning, we'll hear the presentation from Gojko about designing serverless functions, and after that, we will hear the presentation from Bogusław about DynamoDB and single table design. So I think we will just start from Gojko and his presentation, and enjoy the session.
Excellent. So I have to apologize upfront if this is lagging a bit. When I connected 10 minutes ago, it looks like I'm currently having some problems with the internet connection, and maybe people around me are streaming Netflix too much. I don't know exactly what's going on. So if this is lagging a bit, I really do apologize. Hopefully the session will be recorded, so you'll be able to see this better. My talk today is going to be about designing serverless functions so they can evolve easily, and they can very easily support you in development and reduce the cost of maintenance. Serverless functions, the original promise of the whole thing was that we can basically rent operations from Amazon, and that we can get them to do 99% of DevOps and move faster, go to market faster. And some research I've read a few years ago was from IDC was that kind of companies adopting serverless deployments generally tend to reduce about 2/3 of their operational costs and double the speed to market. So designing functions to be able to evolve them easily, designing functions so we can move at high speed is really critical at this point, so we can get the benefit of that. And just migrating a massive piece of monolithic infrastructure to a Lambda function or something like that is not really going to do the trick. Although you can do that now very easily, but that's not really where the big benefits are. And what I'll be talking about is based on two applications that I'm working on. One has been live on AWS Lambda since pretty much mid-2016. In February 2017, we've completely killed everything else and moved it completely to Lambda. And this is a mind mapping collaborative application called MindMap that kind of looks like this, where it's mostly aimed at school children who can create spider diagrams like this and mind maps and collaborate live on this. And what we get from Lambda and the whole serverless infrastructure for this app is just kind of crazy scaling on demand. The usage patterns are very spiky. Children can collaborate with their teachers at different times. There might be lots and lots of people accessing a single document. If they use it at a university, for example, and a popular lecture professor online advises people to collaborate with them. So massive spikes, very spiky, unpredictable loads, and generally we get not having to worry about all of that. The other application that I'll talk about that I'm building now is called Nerakit. It's a system that helps people automate video production very easily and create narrated videos with text-to-speech easily. And it can convert stuff like this, that's kind of like a markdown document where you give it a size, you give it some kind of music in the background, and then you tell it, go and pull out 10 seconds from this MP4 and then read this out using neural text-to-speech, and it kind of creates videos. So what I get from serverless functions for this application is, again, being able to delegate most of DevOps work and most of operations work, most of admin work, and really just focus on the business functionality and getting time to market really quickly. And for those of you that don't know what Lambda is, this is kind of an AWS user group, so I assume some people are not fully aware of all the AWS services. Lambda is Amazon's way to execute code on demand, where you just package a bit of code and you tell it what events to execute it on. And the events can be almost anything in the Amazon cloud. You can get it to execute these functions when a web API request comes in. This is usual for HTTP APIs, browser clients, REST APIs, and things like that. You can also connect it to message queues. So if a message comes into the queue, you can tell it what code to execute. You can connect it to a lot of storage changes. For example, when a new file appears in your S3 bucket, or when a DynamoDB column changes, it can also call a Lambda. And Lambda functions at this point are becoming kind of a universal glue for AWS infrastructure. Recently, they have enabled functions to run inside CloudFront, where you can execute stuff. And generally, it's a very, very good way to plug your business code onto the infrastructure, because the Amazon's promise with Lambda functions is that they will take care of operations, they will take care of capacity planning, they will take care of scaling up and scaling down. And the pricing model is per request, which is really, really interesting from a perspective of being able to operate multiple versions of the same thing. For example, with container-based infrastructure or with kind of EC2-based infrastructure, if you want to set up a testing and a development environment and a production environment, you typically have to pay 3 times the cost of a single environment. And that's why people almost never set up a testing environment that's the equivalent of production. Because Lambda is priced per request, and you have 50,000 people coming and you send them all to a single version, that costs exactly the same as sending them to 20 different versions. Or if your testing system is not being used at the moment, it doesn't cost anything. So it's very, very easy, for example, for people to set up one testing environment per developer or per team, and it doesn't really cost that much. So although kind of this is very simplistic, things with Lambda can get quite complicated, and people can get lost in the forest of kind of messages being triggered and being fired and things like that. One of the use cases I'll show you today is what we do for mind map collaboration, and we'll explore that a bit more. So we have clients from mobile devices, from computers, from desktops, from laptops, uploading changes to documents directly to S3 buckets. And this can be massively, massively, massively parallel. So the hundreds of thousands of users can together kind of hammer the S3 bucket. S3 is going to take that, no problem at all. Then when changes to documents appear in the S3 bucket, Lambda functions will wake up to process these changes, and then they aggregate stuff using Dynamo. They will figure out what are the watermarks, what are the changes they need to apply, and things like that. Then something else will fire when Dynamo changes the records. And then we have a completely different set of Lambdas that then uses the API gateway WebSockets to send updates to clients. And this can get quite complicated. You'll see the whole workflow later, but in terms of performance and scalability, it's kind of totally ridiculous because we get crazy, crazy, crazy performance out of this at massively high scale, and we pay for the whole infrastructure a few $100s a month, which is like totally insane. So that's kind of the promise of Lambda functions. And when I mentioned that things really need to be redesigned up front to be properly using this model, I think there's a couple of things people often miss out on when they start migrating existing applications to Lambda, primarily because they start thinking about Lambda and serverless as another type of application server, where with a 3-tier architecture, you typically have a client, we have an application server that maybe has a web server there, and then there's kind of some database or storage. And yes, you can in theory use kind of Lambda functions like that, but that's not really going to give you most of the benefits. And I'm going to talk about some constraints with the Lambda infrastructure for people that have kind of not done that before. And I'll also show you some interesting tips and tricks, what you can do to squeeze crazy performance out of this, and to make it very, very easy to maintain and evolve functions in the future. Just as kind of a point of reference for this mind mapping application, it's kind of being developed, maintained, supported, tested, and kind of sold by only 2 people. There's me and another colleague in the company. And we are competing with companies that are several orders of magnitude larger than us. And we can do that as only 2 people, although we need to do kind of pretty much everything from pre-sales to support and development and everything else, because we can farm out most of the stuff that's not our core business to Amazon. And this is, I think, one of the amazing promises of this whole infrastructure. So one of the big challenges moving to Lambda or even thinking about Lambda is that kind of even hello world gets too complicated. Not in terms of the code, but in terms of operations. And if people don't really understand the model behind it, sometimes they make stupid mistakes. So I kind of like this acronym MAD HTTPS, but kind of not the HTTPS you expect, because even kind of the simplest single Lambda function deployment ends up being a fully managed, fully auto-scaled, fully distributed, high-throughput transaction processing system. And that's interesting from a perspective of designing good code, because most people in our industry, especially kind of if you start doing stuff cloud native and by moving more from a front end, have not had experience designing high throughput transaction processing systems. That's kind of a very, very niche thing you usually see with banks, with large insurance companies, with large gambling companies. And in my previous life, kind of before the cloud and everything, I was a kind of architect working on these systems and a developer working on the system. So my thinking about this was always kind of applying good practices from these very, very highly kind of distributed throughput processing systems, throughput optimized transaction processing systems. And that's why we've been able to get so much value out of Lambda. What I mean by all this, first of all, the infrastructure is really managed for us as developers. The infrastructure provider, in this case Amazon, or if you're using Google Cloud Functions, Google, or Azure Cloud Functions, Microsoft, deals with most of the stuff that would be called operations. they deal with routing requests, they deal with scaling things up and down, they deal with monitoring, they deal with restarting things that failed, they deal with managing HTTPS and managing kind of security around this stuff and authorization and all of the stuff that basically people often have to do themselves when starting up a bunch of microservices on containers. And there's good stuff, there's lots of good stuff about it, but there's also something that's kind of a bit challenging because there are some constraints of this infrastructure that you might find limiting. And knowing what type of constraints exist there, especially around routing, is important for how we design stuff. The other thing that's important about the serverless, especially on Amazon, is they are in charge of scaling. They being the cloud provider, Amazon in this case, you can't really do much about that. You can set up some constraints, like you can say, I never want to have more than 5 copies of this function running. Or you can now say even, I want to have at least some copies of this function running so it can serve requests. But generally, kind of Amazon does most of the capacity planning and scaling and management. And that has some interesting impact on how we need to design functions to allow them to do that well. The next is, there is no real kind of singleton monolith here. People try very often designing monolithic things expecting that they can deploy a single function, it's going to work on a single instance, but even if you limit it to at maximum 1 instance at a time, that's not really 1 instance at a time. It's 1 instance per version, and as you deploy, it might have multiple versions, you might have multiple concurrent processing versions at the same time, and that becomes really, really tricky if you want to have data consistency and you're doing something crazy with data. And kind of lastly, Lambda is truly optimized for throughput. It's optimized for massively, massively parallel independent operations. It's not really optimized for lots of kind of dependencies and waiting on the network and things like that. And you might get into trouble if you try to do that. So it doesn't really replace a application server. Apps have to be redesigned for that. And the way I kind of like to think about structuring code around this stuff is to think about coupling in terms of deployment and coupling in terms of communication. If we have multiple functions that need to collaborate, if I have, for example, something that needs to save a user to a database and something that needs to start a payment when a user is saved to a database, then there's a couple of types of coupling. There could be deployment coupling that these two things have to go live at the same time because they're quite close tied in terms of the data model they use and the types they use and the data one function expects in the database from another. And they might also have communication coupling in terms of data formats, but not necessarily going live at the same time. They might rely on the same protocols of information and things like that. So there's 2 good options here, really. If you have something that's very tightly coupled in terms of communication protocols and it needs to go live at the same time, then a nice monolith is the best solution there. It will be deployed easily. You can manage it easily. Lambda's are probably not good fit for that as an infrastructure. EC2 or Fargate or something like that probably would be. And then there's this kind of corner up here where we have something that is relatively loosely coupled in terms of deployment. We can launch this function without deploying new versions of all the other dependencies, and kind of the protocol we use between these functions is relatively loosely coupled to allow us to do that. Then you get really easy evolution. And I was chatting about this at a conference with somebody who worked on Erlang for a couple of decades. And he was telling me how pretty much everything he's hearing at conferences about serverless and stuff like this is trying to kind of reinvent and reapply a lot of what was already discovered in the telecommunications world, because massive telecommunication systems are high throughput transaction processing systems. And they're optimized for high throughput and things like that. And I'm really sorry I forgot their name, but the person had a brilliant statement. He said kind of, one of the most important things about designing for a distributed high throughput transaction processing system is to get the protocol between components right. If you get the protocol right between the components, you can afford to get almost everything else wrong. So if we have multiple functions and they need to collaborate in some way, and we get right the messaging protocol between them, then we can very easily remove one, replace it with another one. We can have things that are less performant and optimize them in isolation. We can monitor and troubleshoot very easily. And this app, that mind map that's been live since kind of mid-2016 on Lambda, we have done stuff that's totally crazy, like ripped out bits and pieces and rewrote them from scratch with a lot of confidence, because we knew that it would be nice and self-contained, and that we can always kind of save ourselves the problem because we got this protocol really right. So that's kind of what I talk about, how to get this protocol between the components right. And there's a couple of important constraints. The first important constraint is that when you're running on AWS Lambda, you're really running on a shared managed network. And there's a key problems with that. First of all, network latency is not something that kind of should be ignored, even among kind of between the components in Lambda. So I see very often people launching lots and lots of Lambdas and then using remote procedure calls between them, synchronous invocation, where one function invokes another, waits for the other to complete, and then returns the results. And this is very easy to do because Lambda provides this kind of abstraction around this stuff, but that doesn't necessarily mean we want to do that. And talking to lots of external resources slows functions down because we're going over the network. Long, durable connections are very, very problematic when you have lots and lots of stuff going on at the same time, because the laws of probability say that these things will get disconnected. You might get clients disconnecting. You might get kind of network storage being disconnected. You might get the database to disconnect and network connections interrupted. And it's just a fact of life working in a shared managed network. These things do not happen often, but they happen enough that you need to care about them. Now, luckily, Amazon provides some very, very good tools to manage this stuff, but we have to design our functions to work well within that environment. We need to design them for fault tolerance, and ignoring that there is a network doesn't really help anybody. So try and avoid kind of remote procedure calls as much as you can, and try and avoid synchronously linking things. One of the most common ways you can use Lambda is to put an API gateway in front of it and get clients to connect to it using REST APIs from a browser or a mobile network, as if it was a web API. And API gateway introduces a 30-second limit there. And very often, kind of doing consulting and looking at people's systems, I see people hitting that limit because they get a API call that takes longer than 30 seconds. Lambda can run up to 15 minutes. And then Lambda runs for, 5 minutes to do something. API gateway kills the connection. You don't know that happened. The clients lost the connection and everybody's in trouble. So one of the kind of problems with this is the infrastructure is completely managed, and we need to plan for Lambda functions being killed by Amazon at any point. And really designing the system so that it can die almost at any point and restart and continue working is really important. And the other thing is, in a multi-step process, because Amazon can kill kind of a function at any point. Again, this does not happen often, but if you have millions of users, it happens often enough that you need to kind of deal with these things. You can't really assume that the stuff will survive. And I think this is generally, anything in the cloud, you can't assume it will survive, but Lambda functions are really transient and designed to be transient. So, for example, on the top, I have this kind of mock of a 3-step process where we save something to user database, we call another Lambda to start a plan, and then we send an email to a client. There's a ton of stuff that can happen there. There could be an exception with the database. not being available at the moment. There could be a problem with the Lambda host environment between the two steps. There could be something that, after we start a plan and we try to connect to S3 to log something, S3 just gives us a lot of latency and the Lambda timeout runs out and the email doesn't get sent. And kind of designing stuff like this is really problematic because there's multiple side effects to it. And generally what I would suggest is you have one mutation or one side effect per function. You can read lots of stuff, prepare, and then have one side effect per function. And ideally, if you do need to have a side effect, make it an event that gets published somewhere. So there's generally, when designing high throughput transaction processing systems, I strongly recommend people move away from the idea of kind of remote procedure imperative calls and things like that to the idea of a bunch of events happening. So rather than saying, I start a plan, I do this, I do that, I can say, well, a user registered. Whoever needs to care about the user registering, do whatever you want to do with that now. And the user is registered with a free plan. What's nice about the difference between these two things is we can then hook multiple different things to the fact that the user is registered. So I can say, well, I'm in parallel going to start their subscription plan and send an email. And I might have different retry policies. I might have different execution policies. I might have different scaling or performance policies on these things. And by causing one side effect at a time, we can chain up these things so they work very nicely. So generally, when designing a workflow, when designing this protocol for communicating with the functions, you really want to play like the hot potato game that kind of children play where they pass something and you can't really hold on to it very quickly. And design your functions so that they don't have to hold on to a request for a long time. In that regard, you don't really care if Amazon kind of kills something between the requests. You don't care about multiple effects there because you're reducing the stuff. And your infrastructure becomes a lot more fault tolerant, a lot more resilient. And if you design it like this, then you can work around a lot of these API gateway limits. For example, here's a very, very common pattern we often use. We use this on MindMap, and I use it on Aggregates as well. So a client needs to make some kind of longer request. For example, with Aggregates, people upload a script file, and they need to wait for a video to be built. Sometimes this might take minutes. Sometimes this might take even hours, depending on how big the video is. 30 seconds through the API gateway is definitely not enough for this. So what kind of happens usually, and this is a very common usage pattern, a client makes a request to Lambda. That Lambda is very, very quick to kind of just load up the user's data. Like, what plan is this user on? What are their limits? Can they convert this file? Can they not convert this file? Do I need to charge them more? Do I let this request go through? So there's no mutation here. This is kind of just reading stuff first. And then Lambda publishes a request to an SNS topic. And at the same time, Lambda generates a security signature for a specific object on the S3 bucket. And this security signature allows the client to directly go and pull this file from the S3 bucket without even touching Lambda. So Lambda will send the security signature. This all happens in the matter of milliseconds, and it's fully retryable from the client if the client needs to retry. Well, after the client has a security signature or signed request, basically signed GET request, the client keeps polling the S3 bucket for the result of the job. And what happens in the background, this kind of message topic sends a message saying, look, I have this video conversion task that I got from a client. Can somebody please handle this? And that's it. One of these Lambda functions wakes up in the background, starts processing stuff, starts loading things. And at some point when the request is complete, they will upload the results of the task to the bucket where the client polling for this stuff will just retrieve it, and everybody's happy. kind of in that sense, this lambda, there's two types of lambda functions. One lambda function is just responsible for assigning a task ID, validating that this is a good task, and then kind of causing an event, like somebody uploaded a file, somebody requested a conversion, and kind of all of this other stuff happens in the background, where the client is polling S3 that is insanely scalable, insanely cheap, and you're not even paying for kind of processing time there. So one of the key things moving away from a typical three-tier architecture to lambda functions is to really push orchestrations out of your application layer. With normal three-tier architectures, orchestration is in the application server. We kind of get the client to send the task to the application server. The application server talks to all these other components and coordinates everything, and the application server is busy all the time. You absolutely do not want to do that with lambda functions. You want to decouple it so that Amazon can manage this thing better for you and scale it in different ways, because maybe these conversion requests need to scale differently. For example, we use the same pattern for mind map for file exports, where somebody might be requesting a PDF export or an SVG export or a Markdown export, and all these functions have different demand limits, capacity limits, and things like that. By basically decoupling this, we can let Amazon scale this thing much easier. So there's a couple of typical ways of orchestrating lambda functions, and I'll just tell you my three favorite ones. The first one is to kind of use platform events. This is really good for minimizing the number of side effects you need to do in a single function. So for example, instead of uploading a file to S3 and then causing something else, the lambda function can just save something to S3, and another thing can wake up from an S3 event that the file was uploaded. Very similarly, instead of changing something in the database and then doing something else and then doing something else, you can just change something in the database and then cause an event from the database to continue working on other stuff. The reason why that's good is we get a lot more resilient stuff. We can get retries, we can get much better execution policies and scaling policies, and we can coordinate these things much more interestingly in different ways of scaling. I'll show an example later. And kind of we have SNS and SQS as two other options. So SNS is really, really great for fanouts, where you want a single event to potentially go to multiple listeners. And you might want to filter out who does what based on this. SNS is really great for task-based stuff where multiple handlers might wake up at the same time, like this. A user registered, so we need to send an email, we need to start a subscription, we need to kick off a user onboarding process. All of these things need to happen in parallel. And SNS can deal with all of that for us. And the nice thing about SNS is it will automatically retry if your Lambda dies. So if your Lambda throws an exception, there will be a retry immediately after that, a few seconds later, because Amazon thinks first it's their problem. Maybe the function ran out of memory, or there was an infrastructure problem, so they will immediately try again. And then if there's another exception, they will pause for, I think, about a minute or something like that, and then try again, thinking that maybe there's an external resource busy, like S3 is timing out or Dynamo is timing out, and you're trying to connect to that to give it time to recover. And then after 3 times, it basically says it's not our fault, it's your fault, and then kind of fails the function. And when the function fails, you can send the failed request somewhere else. That's called the dead letter queue. So here's an example that we use very often. This would be from this task thing. So we have a filter on task type of payment requested. We want to initiate the payment. And you can do these policies to attach multiple listeners where they can react to multiple things at the same time. And this becomes very, very flexible to coordinate multiple functions. And then what you can do is you can create and configure external error recovery even. So you can say, after 2 attempts, send this thing either to an SNS topic or send this thing to another function. A very common pattern we use is have an external error recovery mechanism to prevent ourselves from deadly bugs. So imagine you have a payment function and you deploy a new version of the payment function, there's a bug there. And because there's a bug, the client doesn't even know if the bug happened or not. Because in this case, the function controls itself. But with external error recovery, we can have a very, very simple process that just says, look, this task failed 3 times. I'm going to send the client with this task ID a message that something failed. So in that case, going back to kind of this picture here, we would have one function that's this payment initialization function that processes the request, but we could also have another function that says, if any request function died 3 times, just send the client that this request ID failed. So we can have external error recovery, which is really, really amazing. And what we can also do with this stuff is we can cheat death. What I mean by that is Lambda functions are limited to 15 minutes runtime. And one of the things that this video build tool does is allows people to convert PowerPoints to videos, where it will export different PowerPoint slides. We have people uploading presentations with thousands of PowerPoint slides, including videos and things like that. And this does not finish in 15 minutes. So we've created, the way I programmed it is re-entrant. When Lambda wakes up, it says, am I actually being woken up as a retry of a failed request? One of these 3 things. And if so, I'm going to try to resume where the previous function stopped. So immediately after, instead of just 15 minutes, I get 45 minutes here. But after 45 minutes, this thing dies totally. However, I can send the failed request to another function. And I send it to a function that's called resubmit request. And resubmit request function just goes back and enqueues the same request again. So in this case, basically, we're cheating Lambda death. And that's a very interesting way of working around the limits of the platform. As long as you can make your function re-entrant, you can make crazy stuff like this. So very often people try to do really complicated offloading to Fargate or to EC2 for things that don't fit in 50 minutes. But if you can make it re-entrant, this is a very, very fun way of dealing with that, an easy way of dealing with that. And I mentioned dead letter queues. You don't have to send it to another Lambda function. You can send a retry to another SNS topic, for example, where something else deals with that. We often have a dead letter queue that's a kind of receiver of last resort. If something horribly fails, we have an SNS topic that just sends us an email, so we at least learn about that and then fix the problem quickly. And this saved us skin more than once when we've introduced really subtle bugs that don't show until kind of people start hammering the system. The other way of coordinating things is with SQS queues. SQS queues are slightly different from SNS topics in a sense that if you have multiple listeners, if you have multiple Lambda functions signed up or something else, only one will get a message published to the SQS queue. And the consumers compete. So what's nice about this is it helps you implement maybe multiple ways of serving the same request. But unlike SNS, where you will get one event at a time, SQS can support batching. It can support delayed sending, which is really nice if you want to retry after 5 minutes or 10 minutes. And one wonderful, interesting function when kind of using SQS queues is SQS has this option to order messages first in, first out, and not deliver them to consumers by unless kind of the previous message by that same ordering ID is processed. And what you can use this for is massive parallelization, but controlled synchronization on different things. And it becomes really, really useful. For example, with MindMap, we might have hundreds of thousands of people editing a same file and hundreds of thousands of people editing a different file. So when people upload changes, we want to process them in some sequence to provide kind of reliable ordering there. But that's really important within a single file. It's not important across different files. So we could serialize everything to a single function and make that really, really slow. Or we could let this run one function per file. And that means that any changes to a single file will always process with a single function in some order. and we'll avoid parallelization on that. But for different functions, we can go crazy parallel. And that's a wonderful way of kind of changing the throughput of the system based on your needs and controlling the parallelization of message processing with Lambda. So what happens actually when clients send a small change, something like add a node to a document, they will talk directly to S3 because that's kind of crazy performance. And I've mentioned this previously, you can just use a Lambda function to create a signed put request, for example. So people can upload to a very specific location. Each user gets their own kind of location to upload, so people can't override each other's files. And we use this platform event then, when a new change request is uploaded to S3, a message is sent to a Lambda function. Now, that Lambda function, instead of trying to consolidate the changes directly, because we might have 3 different Lambda functions firing at the same time for a single file ID, actually sends this thing to an SQS queue, and it says your message group ID is the ID of the file. And SQS will then take care of parallelizing this in a way that there's never more than one Lambda function processing a single file ID. So it might start one Lambda function for changes to file 1. It might start the second Lambda function for changes to file 2, and kind of never send more than one message for the same file to 2 different functions in parallel. What this allows us to do is have reliable ordering, have kind of controlled parallelization. And these Lambda functions then would, when they finish work, update a record in DynamoDB. That's saying, look, there's new content for this file. Listeners need to know about that, whoever's connected here. That Lambda function that changes, completes the file change, does not try to notify clients themselves, because we might need to notify hundreds of different people, and I mentioned one side effect per function is a really good policy. So the only side effect that this function has is it updates a record in Dynamo saying this file ID has some new changes. And then Dynamo kind of causes an update that calls another Lambda function. The other Lambda function then checks and says, okay, I have these 20 people that are listening to changes for this file. And I'm not going to send it to all 20. What I'll do is send it to an SNS topic that's I'll send 20 messages here that's going to distribute this stuff very quickly. And then in parallel, we'll have 20 Lambda functions starting up using API gateway to send WebSockets based to clients. So we might have hundreds of changes going in at the same time, triggering hundreds of Lambda functions that all kind of send to the same queue. Then 1 or 2 Lambda functions process the queue, they pump Dynamo when they finish. And then again, we have enough per client, and we can use these tricks to scale the system completely differently. In a monolithic option, or a kind of when everything is in the same function, everything scales all the time, and you take up kind of copies of resources even if you don't need them. With something like this, you can actually scale different parts of the workflow on demand very nicely, and that can help reduce pricing quite significantly. So another kind of important constraint when doing this kind of routing, and this is true for any type of routing in Lambda, API gateway, SQS, SNS, or Dynamo, or anything, there are no such things as sticky sessions. With sticky sessions on kind of usual 3-tier application servers that have a load balancer in front, you can say for this specific user, always send a request to this instance, and then instances can keep stuff in memory, they can manage sessions and things like that. That kind of stuff doesn't really exist on Lambdas. So if you have 2 users and they call the same function, you might have 2 instances processing these requests at the same time. Then the next request that comes in, well, Lambda might decide to route the request for the first user to the second instance, start up a completely third instance for the second user, kill the first instance. You really have no control over that. So any kind of in-memory caching, any session-specific stuff cannot stay in Lambda. My suggestion is push all the session stuff to the client, because the client has one instance per session, if you can. And that becomes really important then is to design events around consistency aggregates, because we don't want the client to chatty say, okay, I need this, 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 then send the request. Want the client to ideally send everything they need in a single request so we can punch them around. So for example, with these file uploads and things like that, what we typically do is when a user makes a request, the Lambda is going to go to Dynamo, pull out everything that it needs about that request and send it to SNS, including current user limits, including kind of billing plans, including everything that the rest of the system needs to know. So we don't have to run into problems of kind of consistency later on. And this becomes really interesting from a domain-driven design perspective, where kind of people start designing aggregates of consistency. And this becomes a lot more important when we start looking at Lambda functions, especially because when you have multiple instances running at the same time, there really is no sharing between them. And this brings me to kind of another interesting point. Lots of people design code in Lambda functions to be as stateless as possible. And then they miss out on a few interesting tricks, because Lambda architecture is not really stateless. The best way to think about it is share nothing. You can cache things between requests. It's quite possible that you have lots and lots of requests. Amazon will reuse the same instance to process several requests, not in parallel, but in sequence. And you might get stuff in memory from the previous request. That's a kind of design constraint, but you can also use that to optimize, for example, performance. There was a really interesting issue with AWS SDK for JavaScript version 2. Version 3 is coming out kind of now, and that doesn't have that problem. And the AWS SDK was not caching HTTPS connections by default. So if you have a Lambda function that connects to Dynamo, for every single request, it will open an HTTPS connection. And then the next request comes in, it kills the connection, opens an HTTPS connection. And if you are kind of working with Dynamo, the overhead of HTTPS might actually be more than just talking to Dynamo, because Dynamo is crazy performant. So kind of, for example, just turning on the flag to cache requests helped us reduce the average time for processing in this function from kind of something around 600 or 700 to around 300, because we were caching HTTPS connections to backend services across multiple requests. So Lambda is kind of not stateless. There is state there is memory, there's even a temp space that you can write to, but don't use this to manage sessions, use it to manage the context and cache the context. And kind of another interesting constraint is there is no such thing as an atomic deployment. When you have functions, even if they're part of the same application stack, and you deploy them, different functions will get updated at different times. Things like CDK and CloudFormation give you a transactional deployment in a sense that the whole stack update will either succeed or fail. But if you have a larger stack and your deployment takes a while, for example, for this video processing thing, a full stack update takes about 40 minutes. Different aspects of that stack, different functions will get updated at a different time. And for a reasonable amount of time, you will need to plan on multiple versions of your application running and designing for that. Even if your stack doesn't take that long to deploy, there might be 2 different versions running, because you send a request that takes 3 minutes, and then you start deploying. Lambda will no longer route requests to the old function. It will route new requests to the new function, but the old function might still be running to process existing requests. And what's really important about that when designing these things is to design for a multiverse, design for multiple different stuff existing at the same time, even versions of your same function. If you do that, some crazily interesting opportunities open up, and you don't have to worry about lots and lots of problems that can be caused by kind of this highly distributed architecture. So here's a couple of tricks we use when designing functions. So first of all, anything that goes persistent over any kind of longer period of time, more than a couple of minutes, has a format version on it. So what that means is that when we're storing files for users, when we're storing any kind of requests that are supposed to survive for more than a few minutes, we will put the data format version in the file itself. And then when reading, well, I can say something like, upgrade the version to my code version. So if I deploy a newer version immediately or a month later, and I do something backwards incompatible, the new code will upgrade automatically to this, and we don't have to worry about it anymore. The other thing we often do is we will version all the API URLs. So to allow ourselves to do backwards incompatible changes of API versions, every API URL for the clients has a kind of numerical version. And then when we do a breaking change, we'll increment that, and we will keep the old stuff running, at least for a week. So that if we have any clients that have kind of opened an app and continue using it, they don't get interrupted when we redeploy. Remember that Lambda charges you based on the number of requests, not the number of environments you run. So there really, if you design this well, no downside to running multiple versions of your application at the same time, especially if you multi-version your data so that they can collaborate nicely. Another thing we often do is we will add metadata with event versions on events when we publish them. So for example, if I'm making a payment request, I will say this is the version of that payment request as a format. And then when we are handling events, we can do this trick with version upgrades, but there's an even more wonderful trick, especially kind of on SNS and things like that. When you're creating an SNS subscription, you can create a filter policy, like I showed you for an event type. If event version is just a metadata, a message attribute, well, I can say this version of the function can handle versions of payment events 2 and 3. The old version of the function can handle versions of payment events 1 and 0. And I can route this to different functions, keeping backwards compatibility very easy. So if you design your system for a multiverse in this way, one of the wonderful options that opens up is a kind of free canaries. Amazon Code Build has this support for deploying multiple copies of your Lambda functions and then shifting traffic between them. And you can say, deploy this new version and send it 10% of traffic for the first hour. And then, if it's okay, send it all of the traffic. And if you design it for multi-version, you can very, very easily test new versions, prevent yourself from making stupid mistakes, and have kind of operational policies that say, look, I'm going to deploy 2 versions and monitor if I have exceptions in this one. If something weird happens, just kind of roll back automatically. And you get this almost for free if you design the stuff well. Now, kind of to start finishing this off, I mentioned kind of this thing, but one of the things that is still missing here is kind of figuring out how do we decouple stuff from kind of the infrastructure itself, not just in terms of communication and the protocols. And this is where another wonderful important practice for kind of high throughput transaction processing systems comes in. That's called ports and adapters. Alistair Coburn defined the first instance of this, calling it hexagonal architecture 30 years ago. Nat Price and Steve Freeman, when they wrote Growing Object-Oriented Software, called it ports and adapters. So there's kind of different names for it. But the idea is to decouple code so that there's a business logic core that doesn't talk to any specific infrastructure. And then it exposes ports for the infrastructure it needs. And then you can implement different types of adapters for this infrastructure. So for example, I can create a DynamoDB repository adapter that knows how to talk to Dynamo, but I can also have an in-memory repository for kind of my data. And I can use that for testing, or I can use that for kind of switching services. Likewise, I can send an SNS event to it and just kind of create a port that parses this the right way. Or I can send SQS events, I can send tests events and things like that. So when designing stuff this way, what we usually do is we create a entry Lambda file that's kind of the main Lambda file that only does wiring, absolutely nothing else. And the first thing it does is it will parse the message from one of more formats that it's expecting, and then it's just going to instantiate all the different types of infrastructure it needs, and then it's going to send it to a request processor. And this request processor is where our business logic is. And the request processor doesn't really care if it's talking to an in-memory database or Dynamo or S3 or something like that. All it needs is a file depository or a result publisher or a task runner. And what's really brilliant about that is that you can then properly design your app for testability. You can run your business logic unit tests in full isolation before deploying. Testability is something that lots and lots of people have problem with when deploying on Lambda, but doing ports and adapters makes it trivially easy to run all sorts of in-memory business logic tests and decouple that from infrastructure tests that can happen on a totally different level. So I can have integration tests on just the DynamoDB poll repository that's without simulation. I can afford to execute real tests against real Dynamo because I'm only testing one or two operations, and I might have hundreds and hundreds of business logic unit tests. And this becomes really, really critical. We design all our functions like this, that the key benefits are that we can very, very easily swap the sources of destinations for these things. I mentioned that decoupling orchestration and waiting on platform events is really important, but this allows us to design a business workflows without really thinking about what are all the possible types of events we'll get. And then all we need to do is design another parser in another Lambda function and call this. We can also very easily flip between destinations. This allowed us to evolve stuff. For example, we were using S3 for storage, and then we moved to EFS for storage for some functions. We were using Dynamo for certain things and decided to put it on S3 or the other way around. You don't really have to change a lot of your business logic. Your business logic stays the same. All you have to do is implement another adapter for the port you designed. This thing also becomes absolutely critical for multi-versioning. If we're changing a data format and we want to save something in a different format, all we need to do is plug in a different port. Testing becomes really easy, and the whole evolutionary redesign becomes much easier with this. So those are some ideas. Hopefully, I've tickled your imagination a bit. You can read a bit more about this in my book called Running Serverless, and you can find it on runningserverless.com. Thank you very much. Hopefully, this was interesting.
Thank you very much for the presentation, Gojko. I have one question. I cannot see any question in the chat. So if any of you have some questions, just ask it and we will answer. Gojko answer.
Hey, I do have a question. Was my internet working okay? Was it lagging while I was talking, or was it okay?
Yes, it was perfectly fine.
The gods of the internet smiled on us tonight. Excellent.
Yes, just for the participants, we were testing the connection before the presentation, and something was lagging, but during the presentation, everything was really good. I have one question to you, Gojko, because you have talked about decoupling the logic in the lambdas by publishing events instead of multiple synchronous procedure calls. And it is a very valid point and very good idea, but what we can observe that it can lead to many distributed lambda invocations in many places. So the logic of the business logic as itself will be a bit distributed in your system. And my question is, do you extract every single procedure call to a separate lambda function or separate infrastructure component, or do you stop at some point and leave some bits of synchronous procedure calls?
I think so. There are a few places where we allow ourselves to make synchronous procedure calls, but very, very rarely. That's really something of last resort. And I do that, for example, for security reasons, where we have a Lambda function that is the only one that has access to the billing database, and it controls the data models and things like that. So I think the next talk you have is going to be about DynamoDB single table design. And if you have single table design, in particular, it becomes really important for somebody to be in control of the model of that single table design. And distributing that across lots of different functions can cause fun problems. So we have Lambda that's kind of like a gatekeeper in front of this billing database that's really, really business critical. And checking limits or kind of doing some kind of subscription updates and things like that usually is a kind of remote procedure call there. But in those cases, we do try to kind of make that remote procedure call the only side effect of the function. So I think, what you said is fully valid. If you break this stuff down too much, it becomes difficult to track. But that's why designing these aggregate events, designing events around consistency and getting the protocol right is absolutely critical. Because if you get that protocol right, then you have the relatively coarse events. You have an event that says user registered, and then you can say, okay, once the user registered, what are the 5 things my system needs to do about that? You don't have 500 things triggering because we've broken it down so much. So designing these events, designing this protocol is by far the most important thing people need to do. If they do that right, then everything else becomes easy. If you get the protocol wrong, then chaos awaits you. And that's why, again, I think, there's a lot of this we can kind of relearn and re-explore from how people were designing these high-throughput transaction processing systems for years and years and years. We don't have to reinvent it from scratch, because if you look at how people are kind of doing Erlang stuff, how people were doing banking infrastructure systems and things like that, all of these ideas are already there. It's not a particularly kind of new thing. Lambda just allows us to kind of run this stuff much easier and makes that available to everybody.
Yeah, right. Thank you for the answer. I have one more question. Do you have some recommendation about tooling of controlling business traces between lambdas? You can use X-ray, for example, to debug some business transactions.
I use X-ray. Lots of people use lots of different things. I kind of tend to use X-ray because I never really needed anything else. My infrastructure, kind of again with the events and things like that, is designed so it can fit into my head, and then tracing becomes relatively easy, even with console logs and things like that. But I tend to use X-ray if I'm troubleshooting something, and kind of I use CloudWatch very, very extensively with structured logging. And if you design that well, then CloudWatch log insights can be very helpful for tracing what happened where. For people that don't know what structured logging is, CloudWatch allows you to send it kind of JSON stuff almost, and with different headers. So if you're using Lambdas, you don't even have to worry about that, because anything you log to a console that looks like a JSON object is automatically sent with the right header. And then you can do queries on that across different CloudWatch log groups and log streams very easily. So if you log, for example, something with the request ID and you log as it passes through functions, then all you need to do is do a CloudWatch log insight query for that request ID, and you'll see where it went and what happened to it. And that's a very good way of doing stuff that costs a lot less than using X-ray. X-ray is kind of expensive, but X-ray can capture stuff that's not just Lambdas. X-ray can capture an event going to Dynamo or going to SNS or things like that. So yes, kind of. So I know there's lots and lots of tools around for that, but I've never really needed to use more than kind of X-ray and CloudWatch log insights.
Okay. Thank you. We have also a question from the chat that can you recommend some good source to learn designing serverless in a DDD way?
I don't really think that there's a special thing about designing serverless in the DDD way. I think designing event-based systems or designing DDD like DDD aggregates and things like that, all the usual stuff applies really well to this. So any kind of good resource on designing event-based systems, kind of in the DDD way, this usually comes around CQRS and kind of event-based systems like that. So any resource on that is good is good for serverless as well. And this thing ends up being a event-based kind of transaction processing system. So no special need to design it in a serverless way.
Yeah, and you mentioned about hexagonal architecture, which is also helpful designing in a DDD way. So
absolutely, and those are just good design practices that people have been using on distributed systems for a long time.
Yeah, sure. So we have no more questions. Thank you very much for the presentation.
Thank you very much for inviting me to do this. Hopefully it was useful.
Yes, it was very useful, and I'm sure that it is useful for everyone from our community. Thank you very much.
Bye-bye.
So, see you. So we can start the second presentation about the single table design in the DynamoDB. So welcome, Bogus, and you can start your presentation.
Okay, let me just share the screen. Okay. All right, I hope it's visible. Yeah, okay, so let's get started. First, let me introduce myself. My name is Bogusław Buszydlik. I work as a principal engineer at Northfield Bank in Katowice. And together with our engineering team on our daily basis, we're designing and implementing financial services for our customers, which are then hosted on AWS Cloud. And in case you'd like to reach me, just use my LinkedIn account and write to me directly. I will be happy to answer any questions. All right, so what's the plan for the presentation? First, I'm gonna tell you a little bit about reasons why I personally like DynamoDB. Next, I'm gonna present our business case, so the sample service that we're going to implement the database for. Next, we will see how we would do that with the standard SQL approach, just for a contrast. And then I will do some short introduction to the DynamoDB itself. Next, we will find the access patterns that will be required by our application. And then we will design the model, the database model, just by trying to implement all the access patterns that we found earlier. And finally, I'm going to tell a little bit about the challenges that you may encounter while working with the DynamoDB. All right, so let's get started. Why DynamoDB? First of all, it's a serverless service, at least if you turn on the on-demand pricing model, which I highly recommend doing, at least for start. So it means that you only pay for what you use. So only writes, reads, and the storage. If you don't use it, you don't pay. Another really nice thing about it is that you can have exactly the same setup on your dev environment and on your production, and it scales automatically. So yeah, that's really good. And next thing is the lack of network infrastructure. If you think about databases and RDS, for example, you need to, in order to start using them, you need to set up the whole network stuff, the VPCs, subnets, security groups, routing, all of that stuff. And in case of Dynamo, this is all managed by the AWS, so you don't have to worry about it. And also, you don't have to provision any clusters, instances. You don't need to apply any patches and so on. So that's also really nice. Another cool thing is that you don't have to create user accounts inside the database, like in Aurora, for example. So you simply control your access by IAM policies, and that's it. So it's also really, really great. And finally, you only need to create a single CloudFormation resource to get your database up and running. So yeah, that's the things that I like about the Dynamo. So let's present our business case. So we're gonna try to prepare a database for a blogging platform, and the platform should allow our users to publish their food recipes. So we've got authors. Authors can publish recipes. Then the recipes will be grouped into some categories. And finally, our front users will be able to browse the recipes by categories, authors, dates, and so on. So something like this. To help you visualize it, I have some mocks prepared. So here is a web page of a category. So here you can see there is this name of the category, some description, a list of subcategories that you can click to go to, and a list of recipes. And clicking on the recipe would get you to this recipe page when you have also the title of the recipe, some description, list of ingredient amounts, the procedure, so the steps how to prepare the dish, and also some nice pictures. Yeah, and basically that's it. That's it. So if you think about the entities in such application, you might end up with something like this. So it's an entity relationship diagram. So starting from the top, we have authors. Author basically represents our user inside the system. So it's a username, some bio, email address, stuff like that. Then author can publish recipes. Recipe itself contains some photographs, those ingredients amounts I've talked about earlier, and also some preparation steps. And then the recipes are, a recipe can belong to a category. And here's interesting thing, this loop here. So it allows us to create this category tree. So the categories are grouped, create this tree. So we have top level categories, then each of them can have some subcategories, subcategories can have subcategories, and so on. And yeah, and that's it. So usually, if you're designing a SQL database, transition from this step to the table design is really simple. As you can see here, it's basically a one-to-one transition. So our entities became tables. We've got nice primary keys, foreign keys, relations. Everything is normalized. Yeah, and we're good to go. We can query this database using some SQL queries. So, for example, we can get categories, subcategories of a category desserts, despite the typo here. We can get recipes by a given author. We can get recipes ordered by date, and so on. But the thing is that SQL is a very powerful language. So you can also go wild and do stuff like that. So here are getting authors that created at least one recipe with those crazy conditions. Yeah, and while you wouldn't probably write such stuff by hand, the ORMs can produce stuff like that very easily. And yeah, and the thing is that such queries, they require compute power and memory to be executed, and that's a problem. So if you think about a database, at the beginning you have low traffic, so everything is fine. But as you get more users, traffic is higher, then you observe that your queries started to get slower and slower. So here, in that case, you can do some scaling, horizontal scaling, just by introducing more instances and making them read replicas. Then this way you can distribute the traffic and you're good, right? So yeah, but that's not the whole picture, because also your amount of data can grow. So yeah, and when the amount of data gets really, really big, then the queries become slower and slower and slower. And you might end up in a situation when a single query can take a couple of seconds. And in that case, the only way in that case, you can't just add more instances. It won't help. In that case, you need to take a bigger instance. Yeah, and that's a problem. Yeah, so let's see how Dynamo deals with that. But first, let's see how Dynamo allows you to store the data. So basically, it's a NoSQL database, and means that you can store items like this, for example, inside of it. And those items don't have to have any structure. So they can be just a random pieces of JSON objects. So they can have some attributes, some nested lists, objects, and so on and so on. Yeah. So yeah, we have a collection of such items in our database, and how can we access them? So in the simplest version, we can designate one of the attributes to be a partition key. Partition key means that the data can be, okay. In this case, the partition key is a simple primary key, meaning that you can query the data only by providing the value for this key. And the thing is that it has to be the exact value. So in that case, you can query by name of the city. If you provide Warszawa, then you get the first item. Yeah, and in that mode, the DynamoDB becomes a simple key value database. But that mode is a little bit too simple for our use case. So let's take a look at the more advanced one. So in that setup, there are the primary key consists of two components. Now we have the partition key, which is in that case the voivodeship, and the sort key, which is the city. And in this setup, you can do some querying. And how does it work? So first of all, as with the previous example, you need to provide the partition key exactly as it is, the whole value, but then you can do some operations with the sort key. So in that case, we're looking for the cities beginning with letter K in the Śląskie Voivodeship. Yeah, and we've got this result. And yeah, and the querying possibilities are listed here. So besides begins with, we've got a couple of other functions, and you can think of them as operations on strings or on numbers. But as you can see, the list is quite limited. However, this is the only querying possibilities that the DynamoDB offers to us. There's nothing more really. So the only thing you can do is to provide the partition key and do some operation on the sort key. So in that case, you can only search for the cities in a given voivodeship. You can't look for a city across the whole country. You can't use any other attribute for your query, just the sort key. And yeah, that's the key to success for the DynamoDB. It's so simple that it can be very performant in even in very high traffic situations, and it also can scale really nicely. Yeah, one more thing regarding the keys. The partition key is actually used to determine how the data will be stored, where the data will be stored physically. And the sort key is also used for sorting. So if you do queries, the results will be always sorted according to the sort key. Yeah. So let's see how we can use those querying capabilities to fit our data model there. But first, if you go to the one side note, if you go to the AWS to DynamoDB, you can end up in this place. And then you can see that you actually can search your database by any attributes. You can create those, apply this list of filters. You can run this, and you will get the proper results. So how does it work, and where's the catch? Actually, this operation is called scan. And what it does, it goes through all the items that you have in your database and applies those filters, which means that this operation is not very efficient because it goes through all the items, and also quite expensive in case of larger databases. So in fact, you shouldn't be using that in your application at all. It's best to avoid it and to reserve it for some special occasions. And the easiest way to be sure that we're not using it is by removing the action DynamoDB scan from your policy, so that your application is not able to perform scans at all. Yeah, that was a side note. So let's see how we can fit the whole all those entities into a single table. And also that's the key to success. We're using a single table for all of those entities, just to be to allow them to be efficiently queried. So let's see how we do that. Unfortunately, it's not a simple transition as it was in SQL. Here, you need to think first about your access patterns. So the type of queries that your application will need to perform. And then, based on that, you will shape the data in such a way that those queries are possible. So let's think of the access patterns that we have in our application. Yeah, so first, let's start with the categories. We would like to get the category by ID. We would like to get the top level categories and the subcategories of a given category. Next, we've got authors. So it would be good to be able to get the author by ID, get list of all the authors alphabetically. And one important thing from the legal department, they want us to be able to get all of data that a given author has produced in order to delete it at once. So we are compliant, and the author can have his right to be forgotten. Yeah. Next, we would like to be able to get the recipe by author and by the recipe ID, and get all the recipes by a given author. Next, we would also like to get the recipes by category path. And here is this special requirement that maybe in some cases, we would also like to get the recipes that belong to a subcategory of a given category. And we'd also like to get them as well. And finally, we would like to get recipes in a given date range. Yeah. And now let's think how we can model the data to fulfill them. So let's start with the authors. Here we can see the attributes of our item, and the one pattern that we'll be using is that because we're gonna be storing multiple entities in a single table, and to avoid conflicts with the IDs, we're gonna use those prefixes. So all author items, we're gonna be the ID will be prefixed with this author label and the pound sign. Also, we're gonna name the partition key attribute with this PK, with this generic name. Yeah, so as you can see, if we have the PK like this, we can query the author by the ID. So we're ready to go, but let's do one more thing, because in the future, maybe not here, but maybe later on, we will need to have ability to provide the sort key as well. So in the cases when we don't need the sort key, we can set both values to the same value basically, and work the same as if we had the simple primary key. So yeah, and having said that, you can see that we can query the author by using such query. Yeah, so we just provide author # ID of author for both PK and SK, and we'll get our author. So next one, get the list of authors alphabetically. So how to do that? As you can see, this index won't help us to do that, but luckily, DynamoDB offers us this possibility to introduce those global secondary indexes. And the global secondary index is just another way of querying our item. It works exactly the same as the main PK and SK. It just you can have the other, let's say, perspective on your data. You can introduce those GSIs. There is a limit. You can have up to 20 of them in the table, and they also add some costs. So each GSI produces more costs, but it's the only way to be able to query your data efficiently. So here we have introduced this GSI 1, and we picked for the PK the type of the entity, so author, and in the SK we've introduced the name. So as we remember, the SK is also used for sorting. So that way we can query the table like this. So we provide a value for the PK. We just say we want authors, and it will return us all the items alphabetically. And in fact, I can show you it's actually working. Let's go here. Here we have the database. I have provided some fake values, and we can see that we can do queries here from the AWS console. So let's try the first query. So we're setting the PK to this value. Same for the SK. We run it, and we can see we've got one item. And here is my my profile. Yeah. All right, and we can also try the second query. So here we choose the GSI. We type in author here. We run it. Yeah, and we can see that we got the list of the authors sorted alphabetically. There's also a possibility to reverse the order here. Yeah, all right. So we have the authors covered. Let's move on. So next, let's tackle categories. So first, category by ID. We're gonna use exactly the same approach as with authors. So PK, SK, the ID of the category, and we're done. And yeah, question, how to get the subcategories of a category. And we're gonna do it like this. So notice this attribute path. It's a collection of all categories that are parents of this category. So in this case, we've got the category cheesecakes, and it's a subcategory of cakes, which is a subcategory of desserts. And we're storing this path here. So having it here allows us to build the GSI like this. So we can concatenate the parents and form the string with a path. And having path in the SK allows us to do queries like this. So in case we want to get the top level categories, we query by providing empty path. And if we want to get the subcategories of the category, then we provide the path like this. Yeah, and we're good. And I can show you one more thing because I have also prepared an API built with use of Lambda, and this API allows us to perform those queries. So I can show you that the queries for the categories actually work. So yeah, notice that we're getting the top level categories here. Nice thing about this API is that it also, besides the results, it also gives us the query that was used. So as you can see, we're querying the GSI1, we're setting the PK to category, SK to empty path, and as you can see, we got the result with a bunch of categories. So one of them is desserts, so we can try adding that to the path. Yeah, and we get the subcategories. Yeah, and again, we can add this yeah, cakes. Oh, cakes, almost. Yeah, as you can see, we've got our cheesecake category. Yeah, so everything works as intended. All right, so let's move on. Let's move on to the recipes. And as you can see, recipes are quite complex because they got this collections. But in fact, those collections are never accessed directly. We don't have any access pattern that would require us to get photos on ingredient amounts directly. It always goes through the recipes. So what we can do, we can just include those as nested properties of the recipe, and we'll be good to go. But one remark here is that the single item in DynamoDB cannot be bigger than 400 kilobytes. It means that in case of our ingredients, categories, preparation steps, photos, we wouldn't probably exceed that limit. But if you think about like keeping, I don't know, logs, for example, or something like that, something that produces lots of entries, then it might not be a good idea to store it inside a single item. Yeah. So yeah, and our item with nested attributes can look like that. So we've got the list of ingredients, preparation steps, photos, and so on. All right. So let's see how we can implement our access patterns. So first of all, we would like to get recipe by author and by ID, and get all recipes by an author. And we also had this requirement to get all the author's data with one query. So what we can do, actually, we can utilize the PK and SK. And because the recipe always belongs to some author, we can reuse the author PK and put the recipes under that, under the same partition key as author's profile. Yeah, in that case, you can get a recipe by author and by ID, just providing the PK author ID and the SK recipe ID. And to get all recipes by author, you would use such query. So basically the PK is the ID of the author, and we're using begins with function, and we're looking for items starting with recipe pound, and that's it. Yeah, and regarding the GDPR requirement, what we can do, we can actually get all the items with the PK set to author ID, and we will get all the items belonging to the author. I can show you it here in the console. So yeah, we're setting the PK to this value, author pound bogus, and let's see what we get. Yeah, and sure enough, you can see there is this there is this user profile, and then you have this recipe, one of the recipes. Yeah, actually I have one recipe and the profile, so 2 items in total. By the way, here you can see the so-called DynamoDB sequel, so it's a little bit more complex as it contains the data types included here. But yeah, all in all, it's just the results that we are expecting. Yeah, so let's move on. The remaining access patterns, we want to get recipes by category path, so we can do exactly the same as we did with the categories. So we can include the path as the GSI1 SK value. And there was also this additional requirement that we would like to include the recipes from the subcategories, and this can be easily achieved by replacing this equals here with begins with. It's like, as you can see, we have this hierarchy here, and begins with would cover all the subcategories for us. So yeah, easy. Yeah, and the final one, we would like to get recipes in a date range. So what can we do? We can introduce yet another GSI, GSI2, and we can have the SK containing the date. One important thing is here is that the date has to be in such format that allow sorting. So there is this ISO something that is that works best in such cases. Yeah, and then you can query it like this. So you set GSI to PK to recipe, and you can use between to get the all items published between those 2 dates. Yeah, and if you would like to do queries that are unbounded, then you can set the values to the mean value, or the other one to the max value. Yeah, and I can also show you this with our API that actually works. So here are the recipes. We've got some dates. Yeah, the query looks like this. So the the SK is between this one and this one. And sure enough, we got the proper results. Also, take a look at the fact that they are ordered according to the sort key. So they are ordered according to the date published. So here is 1020, 1027, 11.5, and so on. Yeah, and if we omit, for example, to date, you can see that the query produced query looks like that. So we have this max value here, and I can also show you this getting the recipes by path. So here we have, let's say, desserts, and there is like no recipe that is directly attached to this category, but here we can turn on this deep query parameter. And what it does, it changes the operation here to begins with. And sure enough, we get some results. So as you can see, here is this cheesecake from the desserts cakes, cheesecakes category. Yeah. And yeah, basically that's it. We're good to go. So our final design looks like that. And it's also a very good thing to save that table and store it somewhere in your documentation, as it will be probably useful for the future. Yeah. So finally, let's think about some of the challenges related to working with DynamoDB. So the first one is that you need to define those access patterns in order to design the database model. And it is crucial because if you fail to do that, or if you forgot about some access patterns, then you might end up in a situation that adding them later on won't be possible and would require you to reshape the whole database model. And in that case, the only option is to migrate everything to the new model. So that's not very nice. The other thing is the something that we omitted here on purpose is the many-to-many relationships. And unfortunately, this is probably the most difficult thing to model in case of DynamoDB. There are some strategies for doing that, but it's not trivial. And in our example, we could have this requirement to have tags functionality so that you can tag every post, every recipe with some tags, and then you need this many-to-many relationship. Next thing is combining filters. So imagine that we would like to have, I don't know, recipes by a given author, but also belonging to some category. What you need to do then is to have separate index just for that, because you can't use two indexes at the same time. So you need that many indexes, the same number of indexes that you have these combinations of filters. So that's also a bit painful. Another thing is editing. Imagine that we have this database with some recipes, and now you would like to edit the categories, rearrange them or something like this. But because you have a bit of data duplicated in every recipe, you have this path. So what would you need to do would be to edit the categories and then go through all the items that are affected, so all the subcategories and all the recipes, and adjust the category paths there, unfortunately. Next thing is the migrations. So as I said before, in case you need to add some new access pattern, maybe it won't fit the existing model, you need to do this migration. Yeah, and the last thing that is not possible with DynamoDB is the full text search, something that would be probably crucial in a blogging platform. So yeah, that's simply not possible. So what you can do, or you have to do, is to use some other engine for that. I know that AWS have some Dynamo integration with the Elasticsearch, for example. So you need to do stuff like that. Yeah. And yeah, that was it about the challenges. And if you like to learn more about the topic, there are those two big names in the Dynamo world. The first one, Rick Houlihan, who is an AWS employee, and the other guy, Alex Debris, who comes from the community. They both got really great knowledge. They have some really nice presentations available on YouTube. And Alex is also the author of this DynamoDB book, which is the real compendium for the Dynamo. There are all access, all strategies, patterns, that you can use, and they are really nicely compiled and described there. Oh yeah, so I guess that's it. Thank you for your attention.
Thank you very much for the presentation, Bogus. I have one question.
Yeah.
In which case would you recommend to use DynamoDB at the first place? In the general case, you know.
Yeah. I know. For start, I would use it for something really simple, because you have to get used to the working with it. So probably some small service. It's the best way to start. Some without like many relations and some simple access patterns. I would start with that. It also goes very nicely with lambda functions. So because it scales really well the way the lambda functions do, so it goes nicely together.
Okay, but you talk about when to start, yeah? Where to start with your first DynamoDB table or database. But I meant that in which business case would you use a DynamoDB? In which, technical requirements in your project? You face with the choice of the database, and when would you choose a DynamoDB and not other database?
Yeah, okay, it's a good question. I would say, right now I would choose Dynamo whenever it is possible. So if there are like no obstacles for not using it, then I would use it. So if you have those many-to-many relationships, if you have full text search, if you have many entities involved, or if you have like not very well defined access patterns, or the environment is dynamic, then I wouldn't recommend using it. But otherwise, I would pick DynamoDB.
Okay, thanks. We have also one question from the chat. Have you had any chance to implement disaster recovery cross-region scenario for DynamoDB?
Actually not. No, to be honest, I've, let's say, just started using Dynamo for the production. So we have a couple of services using it so far without problems, but that's it. I haven't had any chance to play with this cross-region scenario. How about you, Wojtek? Maybe you had some opportunities.
No, I had not actually. But yeah, it's all about requirements. I had not faced such a requirement to have a multi-region design for the DynamoDB table. Okay, so thank you very much for the presentation. I see that there is no more questions in the chat. So thank you very much once again for coming to the meetup.
It was a pleasure.
Okay, so thank you very much for the attendance, and the video recording is available on the YouTube, so feel free to share the link with all interested people, and see you on the next AWS User Group meetup. See you.